Hi, my name is Brianna Sandoval. I'm joined by Connor, Gabriel, and Peter to present our 152 project, the analysis of a Boeing 747 aircraft. For this project, we broke the aircraft down into a few subcomponents. I analyzed the fuselage structure, Connor the turbine blades, Gabriel the wings, and Peter the front landing gear. We'll start with the fuselage. In this study of fuselage design, static weight, frequency, hard landing, and pressure loads were studied using two sets of boundary conditions and three design iterations of the structure to determine modes of catastrophic failure in relation to displacement and stress. Aluminum alloy 2024 T3 was applied to both the support structure and the skin for all iterations. The first set of boundary conditions held the lowest front longitudinal structure fixed, as if it were connected to the front landing gear, while the lowest back longitudinal support structure was held with rollers in the X and Y direction, allowing the fuselage to translate only in the Z direction or along its length. In the second set, the front face of the fuselage was held fixed while the back was put on rollers, allowing the fuselage to translate in the X and Y plane, but not in the Z direction. While the static test showed increases in maximum stress across the three iterations, which was likely due to increases in weight with each design with the inclusion of additional support structures, each iteration was able to handle hard loading better than the previous. The stress due to pressure increased slightly between iterations 2 and 3. However, the iterations both performed better than the original design. Typical maximum pressure differential between the inside and outside of the cabin at cruising altitude is about 7.5 psi or 0.007 ksi. From the SN curve for aluminum 2024 T3 shown below, that loading is under the curve for all data represented. However, the analysis of cyclic loading was directed using the Aloha Airlines case study. In this case, the aircraft underwent approximately 90,000 cycles before catastrophic failure. So denoted in blue, for both the horizontal and vertical lines in the figure, a loading of approximately 34 ksi would have been needed to reach that failure. Despite the difference in loading, failure occurred not only from that cyclic loading, but also due to the increased salt concentration in the air as it was flying directly over the ocean, and from defective adhesion between joints.
The part that was studied next was an individual turbine fin from the inner ring of the engine. The material that was chosen for the studies was alloy steel. For the first loading condition, a 100 Newton load was applied to the curved faces of the fin directed upwards. The second had a 100 Newton load applied to the faces of the fin directed horizontally, and the third was a rotational study at 1,700 radians per second around a circle of radius 1 3/4 meter. After these studies were complete on the initial design, two design iterations were then implemented. First was a 1mm radius fillet around the base of the fin, and second widened the base of the fin by 1/2 mm. When comparing the results of the studies, we can see that the addition of a filleted base decreases the stress that is endured by the part in all loading cases. So we can conclude that the addition of a filleted base better decreases the chances of cracking and possible engine failure during flight.
The part that was studied next were the wings, which were modeled using aluminum 2024 T3. We used the boundary condition of being fixed to the fuselage and used static analysis on three loading conditions. One where the plane was grounded, the other where the plane was flying level, and the other where the plane was ascending. Two iterations were created to minimize stress and thereby increase the factor of safety and increase the longevity of the part. These were as a result of our analysis. By increasing the model's shell thickness by 10%, we decreased the stress experienced while flying significantly. However, in the second iteration, by further increasing shell thickness by another 10%, the results did not see further improvement and in fact saw more stress while grounded due to added weight.
A static analysis was conducted on our design for the plane's front landing gear. The free body diagrams on the right show the boundary conditions and the load cases used in this analysis. The boundary condition is the fixed plate at the top of the landing gear where the landing gear is mounted to the rest of the plane. The three load cases are an idle load, where the plane is parked and stationary, a touchdown load, where the plane is making a hard landing, and a horizontal load, where the landing gear encounters a small collision during taxiing. The main design issue was the excessive stress the part experienced under the touchdown load, so the design underwent 2 iterations. The first iteration added fillets to the high stress locations on the axle, raising the lowest factor of safety from 0.96 to 1.1. The second iteration increased the wall thickness of the axle, which further raised the lowest factor of safety to 1.53.
In addition to the idle load case of the landing gear, a closed-form solution was analyzed. When simplifying the idle case to a cantilever beam, it was found that the closed-form solution had a stress error of 21.6% lower than the FEA solution and a displacement error of 34.2% lower than the FEA solution, showing that the closed-form solution is not as accurate as the FEA analysis that was completed before.